So let me introduce you the following speaker, Dr. Alexia Auffèves. Alexia comes from Singapore. She's a director of the International Research Lab there. She's a CNRS researcher. She did her PhD under the supervision of Professor Serge Haroche, and she joined the CNRS in 2005. Alexia has a very unusual path in quantum physics. She did an experimental PhD and then joined the theoretical effort, and she's one of the very few researchers worldwide making connections between quantum physics and philosophy, which I'm sure you can imagine there are plenty of questions in this area. But she's also one of the founders of the field of energetics at the quantum level, quantum energetics. I don't say quantum thermodynamics because we're not there yet, maybe, but at least we are at the moment where we can start exploring the energetic transfers at the quantum level. Yes, so she launched the Quantum Energy Initiative, which spans from very fundamental research. You need to understand how energetic exchanges work at the quantum level, to applications where when we try to build quantum machines, we need to understand how the energetic will work. So I'm very happy that she accepted to cross the Earth to join us today, and we are very looking forward to your presentation.
Thank you very much, Pascale. That was a very, very nice introduction because people are already clapping now. You set the standard very high. It's a real pleasure to be here. It's a real honor, actually, and it's also an excellent opportunity to put in the spotlight this very little recent branch of quantum physics, indeed, quantum energetics, which could have been born in the 80s, actually, but the fact is that the questions about how do quantum systems exchange energy and entropy, people started to ask this question very recently. So basically, we have to build two narratives in parallel now, because quantum technologies have exploded. We build one narrative that is devoted to very curiosity-driven questions, and one narrative where we care about applications, and we try to bridge the gap between both. So that's the game I'm going to try to play right now, before lunch, because I'm the last one. I'm between you and lunch. So here is the outline of the talk. First of all, I will spend a long-ish introduction to explain what this field is about and try to position it with respect to, say, regular thermodynamics, to explain to you that it's not really thermodynamics. Then I will present you a very simple framework where we can start to play the game of quantum energetics. Then very simple application, both theory and experiment. And if there is time, I will use the case of optical Bloch equations to compare the concepts that we build in quantum energetics and the concepts that exist in more traditional approach taken from thermodynamics. That's if we have time. And then I will have a long-ish conclusion to speak about the Quantum Energy Initiative and how this stuff relates to more urgent applications. Okay, so let's start with the 19th century. And rest assured, I won't give a tutorial about thermodynamics. It's just I'm going to be cherry-picking here a few concepts, and then I move on. So what does classical thermodynamics teach us? It first teaches us that when a body receives energy, it can receive two kinds of energy, work or heat. Work is an organized energy transfer that happens when the body exerts a force on another body. It's also useful energy. And then heat is a messy type of energy transfer that shows up if the body is coupled to a thermal reservoir. Okay? So two flows of energy, possibly, that arrive to my system. And what thermodynamics also teach us is how can we make use of that? So heat flows from hot to cold. Well, if you are smart, you can extract work from it. This is called an engine. Or you can play the other game. I want to reverse the flow of heat and have it flow from cold to hot. Well, then I need to spend work, and that's called the fridge. And what thermodynamics teach us is to pay the minimal amount of work to reverse the heat flow, or to extract the maximal amount of work from the natural heat flow. And that's called the fundamental bound. Okay? So these are the very high-level basic concepts I will keep with me, and I hope with you if you bear with me all along the talk. So now, 20th century, people from quantum physics have started to play with the concepts of thermodynamics. And this gave rise to quantum thermodynamics. And in quantum thermodynamics, actually, we keep the same scenery as in classical thermodynamics, but we declare that the system is quantum. And from there, we can already play very funny games, like what happens if my quantum system contains coherences? Can I get quantum advantages with this? Can I violate Carnot bound in quantum heat engines? Or how much work should I spend to keep my system coherent against thermal bath? So these kind of questions, you see. And the thing is very cool, but in all these approaches, temperature really plays a central role. Thermal noise. And thanks to Antoine, we've seen all kinds of other noise than the thermal noise we can find in quantum physics. And in quantum thermodynamics, these are also very open system-based approach. I will come back to this later, but the fact is that quantum physics captures many more situations that are interesting to study from an energetic point of view. That's where we can take a step back and see if we can restart, but with more flexible framework. And this is provided by what is known as stochastic thermodynamics. So let's resume this. Now I do have my system of interest, and actually it is so small that the fluctuations that are induced by the reservoir are not negligible anymore. So it follows these kind of trajectories that you see, which are noisy or stochastic trajectories. Now in this new scenery where we care about small systems, what is heat? Heat is the energy that is exchanged via the fluctuations, through the noise. Engine is a little device that allows me to turn noise into a resource. And irreversibility, it signals the lack of control over the noise. So you see these are drastically different ways of seeing the thermodynamics of things at this level. And the good thing with stochastic thermodynamics is that the concept that this field provides us, they are completely noise agnostic. So we can play with these concepts with thermal noise, where they were born, but also with any kind of quantum noise. And this brings me to quantum energetics then. The game that we started to play with a few colleagues is, okay, let's pick up the usual scenery of thermodynamics, but instead of playing with thermal noise, we're going to play with quantum noise. And then the type of question that we are going to try to answer is, can we build quantum engines? Like, can we have quantum noise that behaves as a resource to extract work? What is the cost of quantum control against quantum noise, which is something that is much more useful for quantum technologies? How much energy should I pay to control my system? And obviously, can we derive quantum fundamental bounds? Like, how can I make sure that I pay the minimal amount of work to control my system? And here, the big challenge is that by throwing away the temperature, I basically burn the bridge between energy and entropy. That allows us in the classical realm to have a fundamental bound, and here everything has to be resumed, restarted. So that's one of the big questions of the field. Okay, so now we can try to put a few definitions and a few roadmaps already for this new field. So the scope, as I already said, it's to explore energy, entropy, and information flows between quantum systems and their relations, but now in the presence of any kind of quantum noise. And the methodology that we want to apply is, well, we want to build concepts that are equivalent to heat and work and irreversibility, entropy production, and the like. And these concepts now, they should be operational. We don't want to do pure theory and theorist friends-only party. We want experiments. They have to be fruitful in the sense that they have to unveil new physics, provide new tools to analyze quantum phenomena, and they should be useful as well, so they must have the potential to help us understanding the energy cost of any kind of quantum technology. So that's the slide. There are typically two playgrounds that we can envision for quantum energetics, which boil down to ask the question, what are the possible source of noise I can consider? So on the left, you have a source of noise that you see in chapter 2 of Cohen-Tanuji, the measurement postulate. When you couple a system, you measure it with a classical measuring device, your measuring device perturbs the system, and it brings entropy into my system. So that's the noise that comes from measurement back action. That's the first way to play with quantum energetics. Second way is, well, you couple two systems and you just look at one of them. Then there is entropy of entanglement. So even if the total state of the two systems is pure, there will be entropy in my reduced system. And that's the other kind of noise we can play with. So just a few words about the first type of noise, because I won't speak about this anymore after that. So here we have played a game with colleagues and this spread in the community about looking at how we can turn the energy of quantum measurement into engines. And this gives measurement-powered engine. Again, there have been a few works in the community. Here I highlight a very recent experiment that was done in the group of Benjamin Huard at École Normale Supérieure de Lyon, nicely spotted in Le Monde. And that's the last example where we see how a measurement channel can also give rise to, an engine. But now I'm coming to the second playground, which will be really what this talk will be about today. And so, like I said, a way to bring entropy into a system is to couple this system to another one and to let the two systems interact, and if they get entangled, there is an entropy transfer in the system that I'm looking at. And so to study this kind of flow, the most simple case study is the case of two systems that are isolated. That's a bipartite quantum system, basically. And this picture here, it actually captures many, many situations of quantum optics and quantum technologies, quantum gates, quantum interfaces, quantum meters, quantum resource generators, masers, lasers. So all situations of quantum optics basically can be captured by this. And this will allow us to have an idea of the energy cost of quantum primitives. And from a more fundamental point of view, this can also allow to understand how quantum batteries can operate. So with this now, I'm going into something that is a little bit more technical, but will remain very simple because I like simple things, and go into the details of the framework we can build looking at this situation. So again, we do have these two bodies, A and B. This is a system that is closed, that is isolated. It is evolving under completely time-independent Hamiltonian, which means that there is no energy that is coming from the external world. So total energy is conserved, okay? And now I'm going to add an hypothesis that is not really a big deal, but I'm going to suppose that the coupling Hamiltonian commutes with the Hamiltonian of the system, which means now that actually we are really in a situation where the two bodies, they exchange energy, okay? And the question that we ask is, what is the nature of these energy exchanges? Can I define some work-like or heat-like quantities? And to do this, I'm going to use the fact that at any time of the evolution, the quantum state of my bipartite system, it splits into two parts. One part which is a product, and one part which captures the correlation, okay? Very simple, and that's a unique decomposition. Now, based on this unique decomposition, I can look at the evolution of one of the two systems, say system A, and if I do this little work, I observe that the evolution equation, it contains one term. I don't have any pointer, but you read at the same time. Oh, but I can do that. So one term that is actually a Hamiltonian-like evolution, and it actually captures the evolution of A because of the force B is exerting on A. So it's an effective unitary, if you like. And another term here that contains the effect of the correlations. And now if you use this evolution equation and you try to see how the energy of A is changing, you can also split this into two flows. One flow that directly comes from the effective Hamiltonian, or the force of B on A, and then you see me coming, but that's work. Well, in a completely different scenery, but that's something that comes from a force and arrives without any entropy transfer. Let's say it's a workflow. And the other term here that comes from the correlations, well, there can be entropy transfer. Let's call this a heat flow for now, okay? So this, I want to insist on the fact that these are really process-based definitions. So the work and the heat flows, this is completely path-dependent, and it really captures the spirit of classical thermodynamics in that sense. These are not state functions we are playing with here. And in the classical limit, where B becomes a classical state, then you see that A just evolves unitarily, and it only receives work, which is also something that's quite intuitive and makes sense. Okay, so let's apply this to a very standard situation of quantum optics. First of all, two-mode mixing. So you imagine that your A and B, they are two modes that are coupled to a beam splitter. So they exchange excitations one by one. Then it's super easy to derive what is the effective Hamiltonian of the system B. And what you see is, the effective Hamiltonian on the system B because of the action of A. And what you see is that here, the mode A, it behaves like a classical source, okay? If I look at this Hamiltonian term, which means that the energy that flows because of this effective Hamiltonian interaction, this is a displacement in quantum optical term, which means that basically the work that is received by the mode B, it is simply inducing a displacement in the phase field, and it corresponds to the energy that is locked in the mean field, all right? While the heat that is received by mode B, this is the energy that will be locked in the fluctuations of the field. So with this very simple model, actually, what you see is a direct correspondence between work and mean field energy, which we called coherent energy, and heat and field fluctuations, which we shall call incoherent energy. Okay? So one thing that is, so first of all, this is very intuitive. And second, what is, well, in my opinion, very nice is that from the evolution of the field, you can get an information of how the two fields have interacted. If you see fluctuations that appear in the mode B, then it means that mode B was entangled with mode A at some point. Even if this entanglement does not exist anymore, but the deformation of the field acts as some sort of bookkeeper of the past interactions. And this is revealed by these flows of work and heat. So that's a first case. Second case, which is exactly the same, but I couldn't resist to put this scheme that I've seen so many times in my youth. So everything happens the same with cavity QED. Then I look at the cavity mode interacting with an atom. And if my cavity mode received work from my atom, then my cavity mode is displaced. If my cavity mode receives heat from my atom, then it gets deformed. So that's basically what is carried by this slide. And the last application or typical situation from quantum optics we can consider are one-dimensional atoms, and I will stick to that later on. So first of all, what is a 1D atom? Because I am aware this is a little bit of a jargon. One-dimensional atom is an atom or a quantum emitter coupled to a one-dimensional field. And this is a situation that you find in circuit QED, waveguide QED, quantum emitters coupled to directional cavities, as in Pascale famous micropillars that are sketched here. And here is the sketch of superconducting circuits from other colleagues and friends from superconducting community. So what are work and inflows in this realm? Well, this is the very same story, actually. So first of all, these 1D atoms, they are sketched also by this kind of picture where you have the two-level atom here, input field here, output field here. And then the workflow that is received by the field, it simply corresponds to the change of coherent power that is induced by the atom. And the heat flow received by the field, it corresponds to the change of incoherent power. So super simple, perfect for before lunch. So now we keep that to move on to a very simple application, okay? And the simple application is actually easy to phrase with the language of quantum batteries, so that's what I'm going to use here. So a few years ago, we played that game of considering the case of a qubit, which is going to be the charger that is coupled to a one-dimensional field that's going to play the role of the battery. Okay, and the goal is to charge the battery, so to extract work in the battery. And we start from an initial qubit state that is written like this, so it contains energy, it can contain also coherence, because this angle in the Bloch sphere, sorry. And the battery can be charged or not. If it's not charged, then the input photon rate is 0. If it's charged, then there are photons that are continuously impinging the qubit. Okay? And the extracted workflow in photon units, this is what I wrote just before, so the change of coherent power. Now the figures of merit of this is, well, simply the extracted work, the charging efficiency, where I compare the extracted work to the amount of initial energy in my qubit, and the optimization parameters are the charge of the battery and the coherence in my qubit. Okay? And so with that, we are going to consider two situations. First situation, say the battery is charged. So then there is, like I said, a flow of photons that is continuously arriving to the qubit. So we are going to control the interaction time. And we are going to optimize the interaction time to extract the maximal amount of work. So let's define this optimal work like this. And from there, we consider how this optimal work evolves as a function of the input power. Well, and this we do that for two different initial states of the qubit, but as a function of the input power, it keeps increasing. So then the diagnostic is very clear. The more I input, the more I get, which is a physical translation of on près de corrige, n'est-ce pas? So the mechanism from quantum optics that justifies for it is stimulated emission. So the more I stimulate my qubit, the more chance I have that my qubit emits in the mode with which I'm stimulating it. Okay, so that's just what is spotted by this plot here. We can also look at the efficiency, but that's basically the same idea. And if really stimulated emission takes over, which is what happens if the input photon flow is much larger than the spontaneous emission rate, then everything that I was in my qubit will end up in the stimulating field. Okay? So that's for the behavior as a function of the input photon rate. Now, I told you there are two optimizing parameters, and the other one is this theta angle. So basically, for this situation, Either I start with theta equals pi, which is my qubit start in the totally excited state, or theta equals pi over 2, which means my qubit actually is on the equator of the Bloch sphere, and it carries the maximal amount of coherence, right? Well, let's just look at this situation here, where I don't stimulate at all. You can see that if the population is completely inverted, I get no work at all. Which means, and I'm going to come back to that point in the next slide, which means that a single photon source does not work. A single photon source provides heat with this framework. While if I start with some coherence in my qubit, then I get some work extracted, meaning that my qubit emits a little bit of coherent field. Okay? So the message of this is that the initial qubit coherence, it contributes to work extraction, which is, if you think with like older concepts or more traditional concepts of thermodynamics, a little bit weird, because if there is no drive, there shouldn't be work, but I come back on that point later. For now, I want to focus on this case where the battery is initially not loaded at all, which is the case of spontaneous emission. In that case, like I said, the work extracted in the battery, now this is simply the component, the energy that is locked in the coherent component of the emitted field. Okay? And this, it takes this very simple expression here. It really scales like the modulus square of the initial coherence of my qubit. And this is something that we have called the self-work, because there is no external drive. So basically, this is the qubit that works on itself. And I'll explain a bit later. But for now, you can look at this plot here. And this is actually the evolution of the work extracted as a function of the angle in the Bloch sphere. You can see that here, it's maximal when theta equals pi over 2, because this is the case where maximal coherence in my qubit. It vanishes for theta equal pi, as I was saying before. And if you look at the efficiency now, which is the amount of coherent field extracted divided by the initial energy of the qubit, it goes to 1 when theta goes to 0, which means we are almost at the vacuum, but at least at this point, everything that is emitted, it's almost coherent. Okay, so that's really what is captured by this efficiency figure here. Okay, I had promised an experiment, so here it is, and here I thank again Pascale, who is following me sometimes on roads that are a little bit pioneering, let's say it like this. And Ilse Mayette de Bijveniger, who was PhD student at the time and who devoted part of her PhD to explore these new concepts with us, with the group, and that was actually super stimulating. And so Pascale and Ilse and the other people of the group have done an experiment to explore this charge and discharge of a quantum battery. And the key experimental capacity that could be used in these experiments is the capacity to measure the coherent fraction of the quantum pulses of light. So this 0 + 1 superpositions by developing something that is called a self-homodyne setup. And so I won't go too much into the details, just flashing the narrative of the paper. So in this paper, what is done is we look basically at the quantum dot that is coherently excited at the initial time. Then this quantum dot, which is the charger, released its energy in a 1D reservoir, say. That's the spontaneous emission, and that's corresponding to the charge of the battery I was describing before. And then there is the second step, where the coherently emitted field is interfered with another coherent field on a beam splitter, and it corresponds to the discharge of the battery. So here I'm just flashing the result obtained in the case of the battery's charge, and I want just to come back 2 slides before, so you remember this here, where we look at the work that is extracted as a function of theta. Well, this is it, and oops. And the solid lines are the theoretical predictions, and the dots are the experiments. So we really have an ideal experiment here. The quantum dot in the micropillar, it really behaves as an ideal 1D atom that allows to explore fundamental quantum optics and quantum energetics concept, and in that case, it was the first measurement of the self-work. I'm just advertising for the second generation of experiment that is currently built and that gave rise to this recent preprint, where Pascale and her group were also able to measure the efficiency as a function of time. Now, this is all time resolved. So we look at the coherent power divided by the total power emitted by the quantum dot as a function of time by refining this self-homodyne setup. And this allows us to really do the anatomy of the spontaneous emission process using energetic probes. So this concludes for this second part. I didn't count. How much time do I have?
You have 12 minutes.
Okay, perfect. So now I'm coming to actually a part where I would like to again take a step aside and compare the type of concepts that we build with this very somehow simple and radical situation of two bodies exchanging energy, and a more traditional situation, which is the thermodynamical concepts, okay? And for this, I'm going to use the optical block equations. Optical block equations, they are super well-known equations of quantum optics. They describe an emitter that is driven by some classical light and that is coupled to some thermal bath on the other hand. And these equations, the good thing is that they can really be looked at using both frameworks. So I'm going to detail this right away. I was saying these are canonical equations of quantum optics. They are hardware universal. I mean, you can find them at play in all quantum platforms, basically. And they are relevant for quantum technologies in the sense that with these block equations, you can describe a quantum gate, but you can also describe, if you drive your system continuously, everything related to reservoir engineering. Okay? So this is interesting to understand what are the energy and entropy flows for these specific equations. Now, if you use the standard thermodynamical analysis, then, if you remember my introduction, I was saying they are open system based. And here, this is typically what happens. What is considered in these analyses is the quantum emitter, which is my thermodynamic system of interest. And this quantum emitter interacts with two classical entities. There is the classical drive on the one hand, and there is the bath on the other hand. And then the message is very simple. Well, it takes 40 or 50 pages paper to understand really properly with thermodynamical concepts how it works, but the take-home message in the end, it's extremely simple. The workflow is the energy or the power that is exchanged with the driving light, and the heat flow, it's the power that is exchanged with the bath. It doesn't go further than that, okay? So now we keep that in mind, and we go back to the 1D atoms. And the very nice things with the 1D atom is that they can also host optical block equations. And basically, you find this everywhere in circuit QED, for instance, because when you drive a superconducting qubit, you not only have the driving pulse, but it comes with a cortege of thermal photons that are here and bother the experimentalists. So this is captured by optical block equations. But now, as I told you before, when we play with 1D atoms, we can also analyze the energy flows using the bipartite quantum energetics concept. Because now the field, the 1D field, it hosts both the drive and also the bath. So let's play that game to see how the concepts evolve if I switch from thermodynamics to quantum energetics. So the bread and butter here is the input-output equation that I remind you here, where gamma here is the spontaneous emission rate of the atom. This is the complex amplitude of my field, and this is the energy balance for the field. So the field, the change of the rate of change of energy of the field, I mean, you get the picture. There is a dot on it. It corresponds to the change of power, okay, received by the field. And this is written like this. Now, the difference, I'm saying this before the next slide, but the difference between the closed approach and the open approach, it simply boils down to splitting this quantity into different ways. So if you are in the open picture, you are going to split this, this energy received by the field in these two terms. This term here, which is the workflow in classical thermodynamics, it encompasses the drive. And I told you before, this is the energy exchange with the drive. So if in these approaches, if there is no drive, there is no work exchange. Basta. Okay? So that's basically what is captured by this splitting here. And the heat flow, it depends on the population of the qubit. Now, if I go to the closed approach, which is the approach that I spent the former half an hour to introduce you to, then the way I'm going to split this energy change here is to separate the change of coherent power and the change of incoherent power. And this is the bipartite workflow. This is the bipartite heat flow, okay? And you see actually that the difference between the two approaches, it's simply captured by this, which corresponds to the coherent power that is emitted in the empty mode by the dipole, which we have called the self-work before. And that's the only and key difference between, say, standard thermodynamics and bipartite quantum energetics for this situation, which again allows to compare both, because not all situations allow to do this comparison. We are at Collège de France, so I wanted to flash this slide because actually the self-work is nothing but the energetic counterpart of something that was spotted many years ago, right here, which is dubbed the self-reaction. And the self-work is nothing but the energy contained in the self-reaction. For those who know a bit, I won't enter into the details, but just to see that there are very deep roots, actually, in that scenery. Okay, and that will be my last slide before the conclusion. Let's use this benchmark between thermodynamics and energetic to look at a pi over 2 pulse and the energetics of a pi over 2 pulse. So pi over 2 pulse, we have a two-level system. We drive it, and then we let it relax. And what you see here is the work that is received by the two-level atom, and in the open approach and in the closed approach. And what you can see here is the difference between the two approaches that corresponds to the self-work I told you about before. So here the take-home message is extremely simple. In the open approach, the self-work is wasted, so all this has to be paid by the drive. In the closed approach, the self-work is accounted for, and somehow, but that's for way future application, but somehow there is the potential to save energy that is allowed by the fact that in the 1D atom, we control the 1D field. We have access to it. And it's pretty different than in standard thermodynamics, where the bath is the bath and everything that is thrown in there is lost. So basically, that's really this ability that is captured by this framework. Okay. And now, a few words of conclusion. So first of all, quantum energetics. So I flashed, or I tried to show you that it's a nice new paradigm to explore energy and entropy flows in textbook situations of quantum physics. It provides new operational and intuitive concepts of work and heat, where we do have this nice connection between work and heat on the one hand and mean field and fluctuations on the other hand. And it carries the potential to reduce costs for primitive of quantum technologies because we leverage the new capacities to manipulate energy, and here specifically in one-dimensional reservoirs. Outlooks. So the list is non-exhaustive because I hope we are just at the beginning of something, but the type of interesting research leads I envision here are, first of all, to derive fundamental bounds, because like I said, we have burned a bridge between energy and entropy, but that would be nice to have some minimal energy costs that are guaranteed by the laws of nature. So that can be a very nice thing to look at. Something that we are currently looking at in my group these days is to provide energy-based witnesses and energy-based metrics of quantumness, so such as entanglement. So we have a recent preprint with Pascale about this. Also, metrics of non-Gaussianity. There are ways to define non-Gaussian energy that is a like proper measure of non-Gaussianity, and use these energetic figures of merit to design optimal processes under energetic constraints. So this is something that is also quite stimulating. Obviously, extend BQE to more bodies and any other curiosity-driven research lead that the community may find interesting, and that could one day contribute to the energy cost of quantum technologies. Speaking of which, so that's one possible big picture, the Quantum Energy Initiative. So another co-founder is in the room, like Olivier Ezrati. So this is a venture that started now almost 4 years ago, with a perspective paper, and then a website, a manifesto, a board, a mailing list, and now we are more than 700 participants over more than 120 countries. This is actually right now known also for these beautiful conferences that have been first organized Singapore, Grenoble. The next one in 1 month is in Barcelona. And typically, the call of this Quantum Energy Initiative is to build a new research line. A new research line to estimate, to optimize the cost of emerging quantum technologies. And for this, we need new science. That's what I just shown you, actually, but really at the fundamental level. And we need interdisciplinarity. And this is captured by this little slide here. If you want to optimize the cost of a quantum computation, for instance, you need 3 different kinds of community right now. You need computer scientists who manage the algorithmic cost. So this is high-level cost. You need the quantum physicists who do the fundamental quantum energetics I presented, who manage the low-level fundamental cost. And you need the classical physicists and the engineers that manage the cost, the big one of macroscopic cost of enabling technologies. And now, currently, these 3 communities, they are barely talking to each other, which means that we are optimizing in silo. So we are finding local minima, but the game is to find the global minimum. So that's what we want to do with the QEI. And to conclude, in this business, quantum foundations, they remain essential because quantum is no free lunch. Now we see billions of dollars that are thrown on quantum technology, so this is definitely not free lunch. And the way I like to phrase it is that we need to carve quantum pouches inside a classical world, naturally. And that's a very quantum non-equilibrium situation. And to derive truly fundamental bounds, we should also encompass the cost of the classical apparata around the quantum systems we are playing with. And to use a metaphor I like, the QEI and all this story, this is trying to find the cost of the box around the Schrödinger cat state, the energy cost around the Schrödinger cat state. And that's a very nice incentive, actually, to close one of the biggest problems of quantum physics, to find the minimal cost of quantum technologies. And on that, I will conclude by thanking my group. Singapore is a very nice place to do research. That's the last group retreat, as we like to say, last year. And to thank my collaborators and friends over time. And thank you for your attention.